After having seen this little demo simulation about the spring connecting two masses, or in other words, two point-like masses connected by spring with strong friction around, we can start to make some considerations. In real world, we see often structures of this kind which resemble vaguely something that anyway we could easily approximate or consider also with almost no approximation as a set of two mass points connected by a rigid rod. For example, this case, as if this was made by connecting a heavy mass here and here, being these almost massless. But with the difference that in these situations we see something which acts as a sort of spring, but not a real spring, a sort of spring which exhibits practically a spring constant which we could say tends to infinite, and a damping which again almost tends to infinite, considering that this time there is a real damping sort of frictional force exerted only along this distance and depending on a reciprocal velocity between these 2 points. So actual spring damping. Now, we are not really interested in discussing that rigorously now. Let's just accept it as is. Well, we see that this kind of force, there is some force acting, but certainly this kind of consideration is very vague. Certainly it's evident at first glance that such situation needs more investigation and maybe a whole new formalism. Well, when we see this kind of situation, there is something we call a constraint force, also called reactive force. It's obviously an internal force, thus obeying Newton's third law. We see, of course, such kind of so-called constraint forces even in the situation similar to the first 3D spring demo simulation we did, in which, of course, the only difference is that there is only one point, and this rigid rod exerting a constraint force is attached to a fixed point, for example the origin of our chosen reference frame, through a special kind of joint device. For this case of spring, it's sort of modified version of the universal joint, which engineers will tell you is made this way. Something this way. Very fine. Being, of course, here exerted such kind of constraint force. Despite the difficulty in defining, in describing by words what a constraint force does, of course we should say that it's a force exerted by a sort of device which measures how much force is being applied on this point and applies force of same intensity as the one measured, instant by instant, but applies it with opposite force. Okay, this way it sounds rather vague, and it's time to introduce some new formalism. Despite the complexity and difficulty in formulating what a constraint forces, maybe changing the focus, the way of thinking about this thing can help. Constraint forces are kinds of forces which realize geometric constraints in a practically perfect way. Consider this situation in the two-dimensional version. Assume there is such a constraint force which doesn't allow to this point to change its distance from this attached point. The constraint force when there is a constraint force in a dynamical system made of material points, the presence of this very constraint force, which introduces a geometric kind of constraint, see again a geometric kind of constraint, Certainly, we cannot use anymore our previous formalism of describing our dynamical system as a list of the position vectors of the single material points making up our system. But we must introduce some good old analytical geometry in our situation. Let's consider this example. Because evidently the system, even if there are more points, or a mixed situation, so a mix of constraint forces and not constraint forces, the material points making up the system cannot have any positions. Since constraint forces are anyway such kind of inherently geometric kinds of constraint because they concretize geometric constraints, we must simply change our focus in discussing dynamical systems and start to think of not a bunch of material points closed in an isolated box, but to consider, yes, an isolated box and still maintain our distinction between internal forces and external forces. External force, internal force. But sort to think of the system as a generic dynamical system which can have a configuration. You see this? Of course, speak about configuration because the system can have some configuration, but the material points building up the system cannot have any positions. Thus, the most important thing, the univocus way to define the instantaneous state of the system is to indicate the configuration of the system, from which univocusly would follow all the positions of the material points making up the system. Since from here we pass here is an example univocusly, certainly we must find a way to represent this configuration in a feasible way, mathematically of course, such that with some easy mathematical steps we can immediately come here. Well, this is done introducing some parameters for the system which are called generalized coordinates on most books. We will adopt this word for it, generalized coordinate. When there is a constraint force, the freedom motion of these points is reduced. The number of parameters necessary to identify univocusly the configuration of the dynamical system under study will reduce. When there are no constraint forces, the number of parameters necessary to identify univocusly the configuration of a dynamical system under study is the number of points multiplied by 3, because the only way to identify the configuration univocusly is to indicate the 3 coordinates of position for each of the material points making up the system. When there are constraint forces, certainly this is not true anymore coherently with what we have been saying before, and thus our way of identifying the configuration will change a bit. We'll introduce a so-called vector of generalized coordinates. We'll call it Q vector, which is not a physical vector, it's just a vector containing the values of the generalized coordinates we have introduced. This point here can have any position. That's okay. But let's start from here. This cannot have any position, but positions same distance, so one angle. To identify univocusly the position of this point, we need only theta angle. This is a generalized coordinate. For this, of course, since this can have any position, we are in 2 dimensions, we will need its 2 normal Cartesian coordinates. So, other 2 parameters for our systems, called generalized coordinates, will be this. We have 3 degrees of freedom. Our dynamical system, enclosed in this experimental test box, 2 dimensions in this example, we'll have 3 degrees of freedom. Each constraint force present in the system reduces the degrees of freedom for the dynamical system by 1. We are considering only so-called holonomic constraints. Of course, the very definition of holonomic constraint is such that it actually reduces the number of degrees of freedom. Most constraints which are concretized by these kinds of constraining devices, which we commonly find in the engineering, are all holonomic constraints. These are all examples of holonomic constraints. For example, these are all holonomic constraints. So each holonomic constraints reduce the number of degrees of freedom of the system by 1. In order to find how many parameters we need, we must just take the number of material points making up our system, and parameterization is sort of an art, so actually don't worry. The process of, so to say, defining our constraint dynamical system this way is called the process of parameterization. It's actually very much like playing a Lego technique. We'll understand why. So our position things will be not anymore just a triplet of coordinates, but will be a function of our generalized coordinate vector. Quick example, this will be distance constraint, so there is a distance, we call it r, multiplies cosinus of theta, sinus of theta, basic goniometry. This will be able to have any position, so it will just be x epsilon. Very fine. Formalism works also in 3 dimensions. This case can be parameterized through so-called spherical coordinates. You can consult it on the internet. The position of this material point, thus the configuration of our dynamical system will be 1 point, so at least we will have one entry only. We'll have what? It will be function of q. Q vector will be 2 degrees of freedom, because originally this point would have 3 parameters to be represented its position. For a material point, the configuration of the system is a position, so one constraint, we go from 3 to 2. 2 degrees of freedom, and we have chosen the spherical coordinates to represent it, so theta and phi. Okay, this is okay, and the spherical coordinates are distance, and this is manualistic. Very fine. Okay, so we have introduced very briefly what are constraint forces and how to parameterize a dynamical system where there are constraint forces, since constraint forces introduce geometric limitations to the system, forcing us to move our focus from such a material point based conception to a conception which has a system, the concept of system at its heart, where the system is more important than its component parts, which are material points. When there are constraint forces, even if there are many material points, such as in an approximation, a rigid body, there are many points, but very few degrees of freedom. In this case, the configurations, just for example the position and orientation of the rigid body, something with which we are very familiar with from everyday life. The system is more important than its components, which are material points. Another typical example of a system of this kind, or this one, we have seen how important the concept of constraint force is, called also reactive force. While usually Newton and Galileo are correctly credited with their discoveries concerning the basics of the mechanics, that is, the material points dynamics and the formalism necessary to describe it mathematically, leading to be able to do a procedural simulation, to use modern words. People often also know in which books these people published the results of their investigations, but usually the invention of the first rigorous discussion on reactive forces usually is not credited. Well, it must be credited to Euler. Here, this is a very interesting website when you can have an English translation of the book where he describes the modern thing. Also about rigid bodies, he introduces the idea of a constraint force also, and most of the very modern notation which we use today, three-dimensional graphs, component by component things, and also the invention of the operation of scalar product, that's what we today know as scalar product and vector product. We study so much history at school, but people still don't know who invented the basics of these very important things. So, okay, further investigation on constraint systems was done partly contemporarily by Euler and Lagrange, and lately by Lagrange himself. So we have credited also these inventions, and by Lagrange, of course, most people seem to know the mechanic analytic book, so of course that's usually correctly credited. After having introduced these concepts, we may be asking, is there a general way to find these constraint forces? And when I find the constraint forces, how can I do the simulation of a constraint system? Well, answering the second question is comparatively easy, because obviously when we find a constraint force, if we can find it, it will be sufficient to apply it to the point at each step of the simulation, to get summed with possible external forces which have been applied. The problem is finding constraint forces. Certainly, the concept of constraint force cannot violate Newton's second law. So, let's take one material point example. This must certainly be true, but we know that if there is a constraint, and after we have parameterized in some way the system, the acceleration cannot have any values, but this must still be true. When no external forces act, of course, the only force will be the constraint force, but the presence of a very inertial motion will, of course, produce a constraint force, because motion will be not rectilinear. Thus, obviously, there will be an acceleration. This acceleration will depend on the configuration vector and intuitively also on its instantaneous rate of change, x epsilon theta. Of course, this is whole summarized in the cube vector, where we have put in a list our generalized coordinates, which have an instant, at each instant they have some values, and the rate of change of these, which is quite intuitive. And the instantaneous rate of change, one doesn't have to get confused about this, that maybe just because this is moving, when this moves, the motion of this must be summed up with this. Of course, but that's not a problem, since it allows to determine the instantaneous velocity of the point. It's just okay. Don't worry about these things. We will do a brief and clear summary of the mathematical conventions, notation, and some basic mathematical rules which allow to deal with these concepts. They are not very much. Of course, based on this principle, based on the fact that when there are more constraints, there are more constraint forces, and thus we will have a system of more equations. We can also stop here the discussion about finding constraint forces, since it's a bit a niche application. For this, I suggest to consult books. But there is one important concept here. There will be one equation for each constraint, and Usually a dynamical system, even if having very few degrees of freedom, it has lots of constraint forces, so we would have to write as many equations, as many constraint forces, moreover all vectorial equations, and that wouldn't be very practical. It becomes evident at this point the need to introduce a new kind of mechanics which considers the whole dynamics and gives the whole dynamics in terms of an evolution directly of the generalized coordinates. The problem is that we just don't know how to start. Okay, it's time to go to try to make some more in-depth considerations on generic systems of material points. Although Newton's third law doesn't add any new formalism to the things previously said, it's certainly very interesting because it extended our attention from the dynamics of the single material point to the dynamics of more material points, allowing us to correctly apply to them some forces which acts between a pair of two points, for example ith and jth material point, depending on the distance. Very fine. It allowed us to define a force acting on some of the points. It depends on the distance between two of them. Of course, the distance is regardless of the order of the indexes. It has told us, hey, when there is such a kind of force which depends only on distance, be careful, because if you want to apply it correctly, you have to consider, together with this one, this very thing, Ji. This was very interesting and certainly motivates further investigation on some possible general rules about systems of material points isolated, which undergo only forces of this kind, so forces which obey Newton's third law. These are called internal forces and are reciprocal. That's the meaning of it. So no external interaction, but there are some forces, some internal forces, because for example there are some springs between some of the many points in our system under investigation, and so on. Okay, we don't have much time to deal with this. I'm trying to make it a bit like a telenovela. Usually in books these things are introduced as just rules coming from the nothing, but I'm trying to at least hint at some possible motivations. For example, one can understand that there is a special position in such a kind of system called the center of mass, which is also the position vector. It's represented as a position vector, xcm, whose formula is this one here. Very simple. It's easy to understand that if we calculate its rate of change in time, so the velocity, will be obtained these expressions. Can you read it correctly? So we obtain this expression, mass 1 for a vector v1, mass 2 for a vector v2, plus so on until the nth mass per the velocity vector of the nth point, all divided by the total mass of the system, which is of course the sum of the masses of the single points. We discovered that when only such internal kinds of forces act, this doesn't change. How to prove it is really simple. We don't bother with it. Look it up on a book. Very fine. Just as we started to investigate the dynamics of the single material point in the case when there is no external force, so we started to study it in the completely inertial case when no external forces act and this point is inside an isolated testing box, such as our quiet room. No external forces was all. Its mass, its position vector, and of course its velocity vector. Similarly to how we did this, and considering how far we got applying correctly the reductionism, we try to do the same thing for such a system of points. No external forces, of course, forces which are not internal or external. It's a very simple distinction. we study this. Okay, this is a constant all the time and only internal forces act. We don't have much time to investigate, but you can find also another of these quantities on books, which is called angular momentum and is defined as a sum. It's of course a vector, just as this is a vector, and is defined as position vector product with the velocity vector of the ith point. Of course, originally m is here in the formula, but you can bring it out. That's really not important. This is another quantity somewhat similar to this one, and we will discuss this is also conserved. But the problem is that while these two things allow to discriminate clearly with physical considerations internal forces from external forces, we don't have yet anything to distinguish constraint forces from generic forces. So, okay, we were able to distinguish conceptually constraint forces from generic forces, considering that constraint forces are the only forces which are of completely geometric nature, although they obey Newton's third law. For example, take this point. Take this example here. The rod, modeled as, just considered as two masses connected by a massless rigid rod. This is a constraint, and of course a constraint is concretized by the presence of a constraint force. We were not able to distinguish, so to discriminate with some physical consideration, constraint forces from generic forces. We could say that we have distinguished it when we can find some physical quantity which is conserved for constraint forces but not conserved for generic forces. Very fine, without losing much time, let's say it clearly. This quantity is a very interesting one. It's a scalar and is defined as, for a single material point, of course, let's write it here. The kinetic energy of the m1 point is 1/2 multiplied by the mass multiplied by the very intensity of the velocity vector squared. This way. You can write it this way, or considering that this is actually a scalar product, write it this way. Thanks to Newton's third law, we can discover that when there are, in this case, is just definition falling down from the sky, actually, but we can see that when there is such a situation, when there are two points connected, for example, undergoing a constraint force acting between them, besides actually obeying Newton's third law, obviously, since it's an internal force, of course, that's quite obvious. It's true that obviously the single kinetic energies themselves, called these m1 and m2, are not conserved, but the sum of the two kinetic energies, of course, yes. And to prove this, again, we have to use Newton's law. Obvious, the change of kinetic energy done by this reciprocal constraint force on the m1 point is compensated by the same action done by its pair, the other point. And they compensate because the change in kinetic energy is the same. But, of course, here starts to be really interesting. This kinetic energy physical quantity has also another definition, which is the integral of a force. Let's consider it instantaneously. It says that a small variation of kinetic energy is a force acting on a material point, force vector, which must be a total force, multiplied by the small change of position vector, small displacement vector, delta S vector, this one here. And of course, on a whole path, this would be, of course, an integral, and so on. Look it up on a book. We will come back to that later. And obviously, since constraint forces don't allow any change in position, that ds along this path is always 0. It's also a way to show that constraint forces don't change the total kinetic energy of the system, and there are many points, of course, because they don't work. Considering this definition of small variation of kinetic energy, with constraint forces the very distinction of external or internal is really not important, because even if I assume there is a constraint coming from the external, so from the outside the box, it's sufficient that I'm very careful to take a fixed point which apparently is kept fixed in the reference frame by the presence of an external constraint force, but this doesn't give problems. Just consider that since there is no change of distance by this position along this distance, convince yourself that also in this case the total kinetic energy of the system doesn't change. Now the nice thing comes how to unify this kinetic energy thing with the very fact that always when there are constraint forces, one or more constraint forces on one or more points, one is necessarily forced to introduce those things which we call generalized coordinates. Of course, it's easy to understand that since the very velocities of the points, so the velocity of m1 vector will depend on the state of these generalized coordinates, these instantaneous configuration of them, and the rates of changes. Obviously, since the definition of kinetic energy is this one here, it's obvious that the whole kinetic energy will depend on always total of the system, the configuration of the system, and the rate of change of this configuration vector, which of course is quite intuitive. This is a scalar function which depends on this sort of vector in which we have collected, we have put together all of these generalized coordinates. When there is only one generalized coordinate, such as in this typical case, this reduces to a scalar. So because the vector with one element only usually is written this way. So in this very case, that would be t that depends on this theta angle and its rate of change, which is the same situation as this one here, but a little bit with in a different context. Very fine. Now we have found a way to discriminate clearly constraint forces from generic forces. Forces, generic, constraint, holonomic constraints. And now, without losing further time, we can start to construct the new kind of dynamics which expresses the whole thing in terms of this evolution, because we can do it. The most important thing we was looking for, of course you could say, but this is just a construct, a special quantity like all the others we have introduced, such as that velocity of the center of mass of a system of points, or this angular momentum funny thing. How can we guarantee that knowing this function for a system is sufficient to determine the evolution of the system? This one, since this term would of course determine the whole system, depending the system only on the generalized coordinates. Who guarantees me that? Fine, so we want to come to a formula which allows us to simulate the evolution of the system, but in a way which is compatible with the law F equals ma. Vector, vector, 3 coordinates, which of course in any simulation you would use as vector A equals vector F divided by scalar m. Compatibly with this, but without caring about constraint forces, obeying only to the law, which is observative, experimental, empiric, but then of course proven that the kinetic energy function, which is the definition of kinetic energy, plus as many points as the system has. This expression is true. This doesn't vary this sum for all 1, 2, 3, 4 up to n. This is true also for more complex systems like double pendula. This is fixed point, for example, one joint and another joint, θ2 and θ1. So M1, M2, but you could have, for example, many braces, many other things. And the thing is that the constraints here are holonomous, which we tried to explain before what means. Very simple thing. So we know that the sum of the kinetic energies of the single material points composing the system, as the system evolves in time, we assume no external forces, is constant. So we consider this the total kinetic energy of the system. Remember, the system, not the single point. Now assume that we have a complicated system, but which depends only on one parameter. And we have this hypothetical function, t, depending only on these two parameters. This is the configuration parameter and the rapidity of change of it. But actually these are just two independent variables, because for small times position, we told it's independent of velocity and vice versa. That the kinetic energy doesn't change means that anyway the system evolves in time, stays on the same height. Of course, you come and say intersect it with a plane of fixed height, and it's okay. The height is, of course, the t function in which I plug the q0 and the q dot 0. Very fine, but this is not procedural. The intersection function with a plane like this is horrendously complicated to calculate. Most of the times probably it's impossible. But remember, and it's not local, it assumes to know too much. This whole function assumes. All we know about the function is that we can evaluate it, which is the case. So we find out the value of this scalar function at q0 and q dot 0. I could do the gradient to calculate which is the most pendant, the steepest variation of it locally. Which you would do, the partial derivative of t, depending on q and q dot with respect to q and with respect to q dot. Let's write it like this because clarity doesn't harm. We must be totally unambiguous. That's the steepest thing. But there is one thing. Locally, this is a plane. Here, locally, a plane lies. That's a fact. A tangent plane to the thing. If you do that guesswork, but more rigorously, which we introduced before, we could hypothetically construct this same level curve by stepping. Go from here to here. I get the new q0, q1. I step again. A more complex system we will see later. Very fine. So we could conclude, so by intuition I did this when I was very young and completely on intuition, so this is not stratospherical. We try to formalize this. It means if we hypothetically know one of the legal evolutions of the system, I mean legal, so starting from a combination of q0 and q dot 0 parameters, because at least it's always a couple. Along this, the height doesn't change. What does that mean? It means this. Convince yourself. The variation of height, if you look at the height due to only this locally here at each point, is compensated by the variation due to this. So it's 0. We preserve the initial height t0. Very fine, but this is too abstract. Let's see locally if we could maybe extrapolate a rule to construct this curve from little segments where procedure this way. Of course, we transit to mathematics, what we say by words. I can evaluate this. I have this derivative locally. I do this derivative. We obtain the local plane approximation, which we have been talking about in detail, or we will, be evaluated in q dot 0, q0. Evaluated at the local value of the variable with respect to which we were deriving. Assume this is given a small variation on q. this here. I want to obtain how much variation on q.0 I must do in order to compensate any variation in height. Well, apply the definition. This you divide all by this and you obtain. Then you change, you do q new, and now you are here. You take this, you consider the same names, but you plug in here the new values, and you do the same work, and you will do this. The method is practically functional, but the problem is here not dynamics, of course. How this evolves in time is, well, the important thing is that here it starts to become really useful, the fact that we have considered the polynomial things, and we know also the instantaneous, the instant by instant approach, the expression of that kinetic energy for a given instantaneous configuration, and I have also an initial configuration of this. In order that simulation can be done with this, the passage from this to a Q1 rate of change, before, after, in order that this be possible, this passage must be univocous. The polynomial thing has allowed us to consider that for the passage from this to this one is done already. We already know that it will be 1 equals configuration vector before plus the instantaneous rate of change of the configuration per a very small time step. So that our only concern is to find this 1 equals this q.0 plus some q double dot multiplied by h. We are looking so for a guarantee on the fact that this passage depends only on this one and that it's of course univocous. If the polynomial thing, and thanks to the very definition of kinetic energy and the fact that it's of course the sum of the single kinetic energies, so it's a total kinetic energy for a system of material points such as this one. This is a three-dimensional example. The rigid rod, 3 dimensions is m1, m2 and the massless. The guarantee is looking at what kind of function is t. I must only guarantee that when I position myself at a certain configuration, there is only one, so to say, variation vector, this one, which univocously allows me to pass to another point after having performed this modification, in a way that the height on this function, so the is conserved. Analyzing the very expression of v as a function v ith, depending on these two things, and putting this together with the definition of total kinetic energy, which is the sum of the single kinetic energies, which is sum of 1/2 mi v squared of the ith point, allow you to prove that this function is such a good function that at each position I can univocously identify next configuration which allows me to stay on the same height even if this one is fixed, so that there are no bifurcations. Such situation does never happen. The function is always well behaving, so that you have only at most, in seeing the time evolution when no external forces act, you will always be a very complicated car, of course multidimensional in most cases except the 1 degree of freedom case, but it will always be a univocous car. No external forces act, so the only requirement is that you can do this. But our discussion on polynomial thing, on instantaneous thing, guarantees that this can be done only by stepping from one configuration to the next close configuration, then restarting from here, searching the next one, and so building up a polyline, poly thing, so to say, list of following a succession of configurations which always satisfies these. Okay. Now let's take white paper and introduce some necessary mathematical background for this, since there is this parameter. Is the radius multiplied by this vector, which is very simple, very elementary concept. Cosinus of theta multiplied by r and sinus of theta multiplied by r. One of the most common functions. It's in the whole thing. And okay, in this case, of course, there is motion, so when there is a rate of change of this, we will have a velocity vector. We must consider also time dependence, so this was instantaneous, this was time dependent. Since there is only one parameter, if there is time dependence, to describe how this evolves in time, we must put some time dependence somewhere, and the only place we can put it in is at this parameter. So we are just forced by pure logic, just simple coherency, to consider as this is a function of time. But now we see this moving. We cannot change the distance from here because there's a geometric constraint. Velocity can depend only on the rate of variation of this and maybe on the very value of this. So what is velocity vector? Is the time derivative of this. Of course, this is a composite function, so it's a function of a function as a function of time. Remember a simple chain rule. It's simple introductory calculus. We see that when you try to derive such a kind of function, so a composite function, function of a variable, it's the derivative of this function with respect to this, as if this were a variable, as if these were t. Okay, this is, call it just g without this thing here. Function of g derived with respect to g multiplied by, and here is instead just very obvious, gt with respect to time. Very important not to get confused on this thing. In fact, often it's convenient to write it this way, but okay, you should know both notations, that writing this or writing this is the same thing, because after all it's just a convention. Maybe if you prefer this notation, when here it's clearly indicated that g in this case is considered a variable, a simple derivation rule is applied here and then it's applied again here, but here it's g, the variable considered to be g, while here t. Now this is the composite function derivation, and you must apply it here. If this were cosinus of x, what's the derivative of cosinus with respect to it's from the table of derivatives, it's minus sinus of theta. I have derived with respect to this thing, but I must remember to multiply with respect to the derivative of theta t, which we indicate this way, which means, remember, this thing always means time derivative of t. of theta as a function of t, or any function. Okay, very good. This is the derivative of the sinus is the cosinus from the table of fundamental derivatives multiplied by the very derivative with respect to t of this function, which is theta. We discovered that in order to find the velocity as a function of time of this point, in this case when there is a constraint, we need the rate of change of this. Here is our brief summary in mathematical notation and rules to understand the derivation, the deduction of our new kind of mechanics. So quickly, these are just notation conventions and people often use both without warning. So x dot is equal to v velocity, acceleration is equal to x double dot, x1 dot means velocity, that is ddt, and so on. Often when generalized coordinates are in place, often these notations are confused, because just people often books don't warn, and even I cannot always be sure not to mistake writing. These are all equivalent in our context to get an idea. So for the symbolic rules of derivation and the definition of the quantities such as velocity and acceleration, starting from the parameterization function, is this. This is the symbolic. This is the symbolic one for the acceleration. Since for the acceleration we have to derive again the velocity, we have to derive a product of two functions. When deriving the product of two functions, they must be considered whatever as just normal composite functions, This one first will appear as a composite function, but we must consider it as an ft, and the other is already just a gt, for which we must apply the function product derivation rule, which also has a pretty geometric meaning, which is this one. This picture, I think, speaks for itself. The product of two functions, when we want to calculate the variation of area, there will be three contributions. This one function for the variation of the other function, plus the variation of this function for the value of the other function, and the product of the two variations cancels out, because it's a really small quantity. Very fine. From our symbolic calculations, very confusing, but all deriving from the basic rules of multivariate calculus, multivariate calculus written. I'm sure you can find some good summaries and tutorials on that on the internet if you want to understand the why of these rules and how they work. For one, we have given a geometric meaning. So, having given some proper names to these derivatives, such as the theta dot for the time derivative of theta, and trying to perform explicitly this function where a theta double dot will pop up, after all, we come to our ready instantaneous version table, where we have the usual parameterization function, we have the velocity vector of the material point considered, and we have finally the acceleration. This should be known even if we fundamentally won't have to use it. It's here. It's a function also of theta double dot, because from the application of the function product rule and from the fact that this was already a derivative, it pops up also a second derivative of theta, and so this isn't even so difficult after all. Since we have been bothering so much about polynomial interpolation for dynamics of the material point, let's don't miss to generalize it to also to this case, so that we never won't have any doubts anymore. Let's say from simple deductions looking at this equation, looking that the acceleration is the most general quantity in the dynamics of the single material point, since this is directly proportional to the force applied to the total force, which doesn't obey to any other physical law, it's a given, since acceleration is the ultimate quantity in the dynamics, classical dynamics of the material point. So in order to determine the least degree of polynomial which theta has to be in order to reconstruct around a certain instant very well a motion of a parameterized system, 1 degree of freedom and 1 point, with a polynomial here, which must be realistic, of course, only around this instant, assuming that these points after all are rather close to each other. We will discover that r theta must be at least of this kind in order to be able to express the most general case. So we have this, we need this. We also have a second a theta double dot, so we must have it. We do the usual polynomial. Since this was a vector, we must see then how this will appear when we plug in here this, in order to visualize at once what happens. If we have that kind of theta and we explicit the whole motion of the material point which has this parameterization, we will have this expression here, where of course this was quite obvious. There is the start initial position, then there is also a velocity, this is the time, this is the velocity instantaneously, which becomes a coefficient, and now the acceleration coefficient, which is a bit more complicated as we have seen, but of course it's just simply put as a coefficient of the third term of the polynomial, approximating polynomial of this. So such a polynomial, if we have explicited a second degree polynomial, will be faithful to our parameterized system when for the parameter we have this kind of time dependence. And it's also interesting to note, but even we don't we are not going to waste time on this, that this acceleration is split spontaneously into two parts. One is familiar and is just the part of the acceleration perpendicularly to this one. So it's the part of the acceleration perpendicular to the instant velocity, and another part which is parallel. I hope you will find useful these notions, a little bit more depth in notions on what these rules mean and how they are used in classical physics. So let's see two important notes. The first is that actually this way of writing a derivation with respect to a time variable, which any function in this case has, even if it's present as the variable of a function of which our considered function is a function, even in that case, when we write this thing, is the same as writing these things. People often use both notations without warning. Me too, of course. It's almost impossible not to get confused. These two things mean the same thing. Just as this means the same thing, and the context must be considered. And the other note is that while doing these funny rules, it's easy to note that this equivalence is just true. The derivative of the position vector with respect to the one parameter equals exactly the derivative of this with respect to the rate of change of the parameter. This comes directly from considering this and giving some proper, more representative names to these to the parameter, its time derivative, first and second time derivative. Of course, also this has a geometric meaning, which also is intuitive. It means that a small variation on the theta, d theta, causes a dx, a scalar, this is a vector, which is equal to, so this is not a big deal, but it's certainly very important. Okay, these were these important rules and notation conventions for the case of one point and one parameter, but later on we will of course expose the generalizations of these rules to the case where there are more points, which actually doesn't add much, and there are, most importantly, more degrees of freedom. These generalizations will be almost immediate, so don't really worry about it, and let's concentrate on the deduction of the new kind of dynamics called the Lagrangian dynamics for the case of a dynamical system which has one degree of freedom and one material point. After this we will see the first simulation done with the new kind of dynamics, which is this one, and then we will progress to more complicated simulations. In the first part of the video we will come up to the simulation of such kind of mechanism. We'll close the first part of the video. I hope you like it. Remember that it's all a bit like playing Technic Lego. Just very fun, and of course in mechanical engineering it's a must, and also interesting from a theoretical point of view. Okay, we know where to start from, and we know where we want to arrive, an expression which certainly will contain this. We start from here and we consider it as it would evolve in time. So from here we pass here. Considering our discussed polynomial thing, we can certainly assume to know these things. We write this equation in a more comfortable way in order to avoid indicating accelerations, since it's something we already want to avoid. We know that when a constraint system is being discussed, such as this one, or any of these other examples, piston and a point constraint to a parameterized curve, or this typical case, rail problem, we know that, returning to this simplest example, the dependence of the xt is of this kind. It depends on a generalized coordinate, whose time dependence we assume to know as previously discussed. We explicit it this way. Okay, nothing new, since this acceleration will be able to take place only in the direction allowed by the constraint. Thus, we know that a more correct way of writing this would be by projecting these vector quantities on such a vector. The simplest attempt to get such a vector would be, of course, the vector which is formed by connecting two points which are obtained by starting from a theta 0 t and varying it by a very little, thus obtaining this vector difference. We know if we divide this by the very d theta we operated, is nothing but the derivative of this vector valued function. So this gives us a vector which is always to the path. So okay, since no information loss is introduced by doing this projection, we just multiply both parts of this equation by this quantity. The fact that the length may vary is not a problem, since by multiplying the same quantity both sides of an equation, it anyway doesn't change the result, doesn't violate anything. So we write down our result multiplied the left part of the equation, obtaining this, and the right part, obtaining this. I explicited the dependence of the v, whose expression we revive here, which becomes a v as a function of theta t and theta dot t, as I clearly indicated here. Both sides appears this ugly equation. We can give to it a proper name g. Recalling some basic rules of calculus, of which we have explained before, briefly, this is suspicious. This has very much this form. Taking the general product rule from basic calculus, we can realize that we could rewrite this, considering it with these substitutions here, as this minus this, thus obtaining this expression in which we substitute our names which we gave, obtaining this. Very fine. Now we have an interesting expression which we try to manipulate in order to get something similar to at the end. Okay, we rewrite our result and we start to think about how we could rewrite some of these things in order to get what we want. Expression which shall look like this. One important observation is that this expression here equals this. Velocity will be certainly needed, so we immediately replace it here. We are already a velocity multiplying a velocity. Let's don't care about this, but we have two velocities. That's good. Other important thing that we proved was that this simply equals this. Just very easy. Since in a way we will need, in a relation, one derivative with respect to the q dot, which in our case is the theta dot, one with respect to the q, we will try to manipulate so that one will have the derivative with respect to q dot and one with respect to q only. Okay, let's see who are the best candidates. Let's see our equation rewritten. We have this. Since this seems suitable for this substitution that makes appear a velocity derived with respect to the q dot, we operated this change. Okay, we have two velocities and a derivative with respect to q dot. Fine. The other member, I operated this substitution, this simple equivalence. I get two velocities and derived with respect to q. Very fine. I have the math m at both, so it's alright. I rewrite it. There is a rule from calculus which says that in this case, if you bring this out, you must add a 1/2. Since derivation is a linear operation, this can be brought inside as well as here, and we obtain this derivative with respect to q dot of this expression. Surprise, it's him. We rewrite it with our conventionals, symbolic, and we have derived the Lagrangian equation for a 1 degree of freedom thing, one material point. Now, since we want to simulate we want to do computer simulations, we want to explicit this ddt, Lagrangian equation of motion, for a 1 degree of freedom dynamical system containing one material point, something which will be very easy to generalize. Briefly, what this geometric only means is this: when no external forces act, this is 0, and we have only this equivalence, which accordingly to we had already previewed has a derivative with respect to q dot and one with respect to q alone, but here there are some quite heavy modifications. In fact, we explicit this, we see some interesting things. This has a time dependence. Verifying this briefly means that when there is a motion, this is the kinetic energy depending on q dot for 1 degree of freedom. So the system keeps the same energy level as it used to have before. However, this path will be complicated. First thing that strikes is the natural stability that the dynamical systems want to maintain always according to this equation, something just very different from our economy, for example, which in my opinion tends too much to just increase activity and don't care about stability. These laws of nature say that stability is better than extremism. When a force is applied from the external world, something which we will discuss far more in detail in the second part of the video, means that the system will go to another energy level, and if the force stops to act, it will stay there and evolve, because this evolution has a time dependence. And now we see, in fact, if we explicit this with respect to time, we can get a q double dot equals expression, and we must do the stepping in order to find configurations of the system from instant to instant. Video game nerd. Okay, you can have a review of this. You can have this derivation explained here with other words in game physics book, written somewhat better, but with a notation which sometimes may seem a bit more complicated, and so on. Let's do our first simulations of 1 degree of freedom systems. In the case of the piston, there will be more material points, but we don't have to be concerned. First thing we can do is just try to apply the Lagrangian equation of motion to simulate this, but considering in this case the kinetic energy is the sum of the kinetic energy of this point and this, and in the Lagrangian equation of motion we will have this total energy depending on this parameter, which is the theta angle. Why we could already be almost certain that this will work the same? Because although this constraint frame is moving time usually, there is Newton's third law acting between these 2 points, even if this is a constraint force. By definition, as we have already mentioned, that constraint force cannot change the total kinetic energy of the system, even if it is implemented in this internal force type way, thus obeying Newton's third law. Since globally the scheme, the way to implement a simulation of a dynamical system with the 2 different types of mechanics is practically the same, only some quite superficial differences, mainly in the formulas, of course, we are going to go quickly through the simulations done with these other Lagrangian mechanics, leaving to the dear viewer, if he wants to consult quietly and in detail the simulations provided, which are available to download on the internet at sourceforge.net. Okay, so let's do our first simulation with the Lagrangian method. Since the Lagrangian is completely careless about whether one works in 2 dimensions or actually 3 dimensions, but cares only about how many degrees of freedom a dynamical system has, let's consider everything by default in 3 dimensions. So remember that this force applied from the external world, which we usually call F with a little x written here, vector, the contribution of these will be here and only here, and the rest will always be the same expression for a 1 degree of freedom thing. Okay, let's explicit this and obtain this formula, which is a standard for a 1 degree of freedom thing. Okay, the parameterization of this situation is this one. Really simple, calculating the velocity by deriving this with respect to time, considering that it's theta t, but of course consider the instantaneous thing, which I try to explain as well as I could. It becomes this, really simple, and the kinetic energy becomes this because bx squared plus v epsilon squared plus vz squared. Very fine. Of course this will be 0, so this is 0, and of course the sum of a sinus squared and the cosinus squared is always 1, and what will remain is only by picking out the theta dot squared, which appears in both expressions. We end up with this expression for the kinetic energy for such a system. This is so simple. For 1 degree of freedom system, one can also plot this graph of the kinetic energy, in this case using of course a math program, also a graphing program. One could easily find out that the kinetic energy of this thing is a sort of, let's draw it. For all theta it's a sort of parabola. In fact, this is the expression here. Very fine. And of course that means that if we start from a certain combination of theta and theta dot, for example from here, if no external forces act, this system will go here, depending on whether it had a positive theta dot or a negative theta dot. Plot this graph while doing the simulation, so to understand how this configuration evolves in time. Very fine. Suggest you to experiment with this thing for some more complicated 1 degree of freedom dynamical systems. As I waste much time with it, I implemented a GameMaker simulation of this, even if this is so simple that it's almost too simple. In this example we have 3-dimensional graphs, but it works also with the free version of GameMaker, since I wrote this 3-dimensional graphics routine as a procedure which eventually manages form this 3-dimensional graph only through drawing 2-dimensional shapes at the end. Perspective, a simple 3D graphics procedure. Okay, we have our ball moving. I implemented that it draws the velocity vector. There are some errors sometimes in this graphics routine, but it's not so bad. In fact, the distance of this point from the center doesn't vary, and we can apply a force. And we see that the point is constrained to stay on a circular shaped rail, or in other words, it's constrained to stay on the same distance here and constrained to maintain the z equals 0 position. In fact, when I apply a force vector which is pointing high, nothing happens. Let's look it from a bit closer. In this case we have the typical pendulum thing, something that resembles a usual pendulum. In fact, by pressing the constantly, I apply a constant force there in yellow, and we have the usual pendulum situation. Okay. We can see The simulation procedure is almost the same, with the difference that we have these configuration parameters. For the rest, everything is the same. One difference is that we really don't need an acceleration variable, even if it may be very illustrative to calculate and draw also the acceleration vector. In the main procedure, we have that it evaluates the total force acting on the material point. Since here there is only one, a friction force included, external force, some interactively applied force, and the frictional force. We calculate the FQ, and then we insert, in this case directly, the formula obtained by solving for theta double dot, the Lagrangian equation of motion. Then the dynamical system is updated, and then the position of the material point constraint is calculated in its Cartesian coordinates, starting from the generalized coordinates. In this case it's only one, which defines the configuration, the instantaneous configuration of the system. Also the velocity is calculated, but that's only for a graphical thing. Actually this is not part of the simulation. In fact, we are left with only these very few things. Very fine. We are not going to prove rigorously the Lagrangian equation of motion for a 1 degree of freedom dynamical system which has two material points in it. In fact, it was already obvious by what I said about Newton's third law that this same equation of motion would hold. And if you look up the proof on some books, such as On Game Physics, will end up by proving the Lagrangian equations of motion for a dynamical system which has moving frames of constraint. For example, this constraint, a rotating joint, and also this one. And the idea is to prove that the same equation of motion holds. But this is simple, a bit boring, and of course the reason why it works is that Newton's third law must be applied between this and this point. Very fine. Now a little introduction to some basic techniques of parameterization, and then let's parameterize this. The idea is one starts from a practically implemented dynamical system, such as a mechanism which I tried to sketch here. One starts from the first fixed point where a joint is put. Very fine. Now one sees which is the first mass, or something we can consider a mass point at the end. This first thing we will call M1. Very fine. One sees the parameterization of, one sees what kind of joint this, and expresses the position of this point with one of these basic parameterization rules, of course. The more advanced we will go to the second part of the video, we will see advanced parameterization techniques. Okay, this is a 2 degree of freedom system, but don't care, we will explain also that. Then, since this was expressed, one can express the position of the next material point with respect to this, considering this as a starting point. One sees this, sees what kind of joint this is, applies the right parameterization. For example, this one writes down that the second material point here, this was actually M2, is actually the first, plus the expression of the parameterization of this. The idea is comparatively very simple. One doesn't have to confuse the idea of a joint with that of a constraint, because we can have a joint even where there isn't any point, while where there is a point there can be possibly a joint, or the system can just have a, let's say, dead end. Some examples can clarify possible doubts about this. Very important thing is that the same dynamical system can be parameterized in different ways, but the dynamics is equivalent, of course, is always the same, obviously. Let's see an example of how to parameterize a point constrained to a generic curve, which we already know what a parameterized curve is. You can also use polynomials to express it. Of course, in our situations, this was actually a parameterized curve, even if a very simple one. I'm going to show you a small simulation I implemented of a point attached on a parabolic curve in a three-dimensional space, to which, for example, one could attach a spring or also put some friction. Very fine. When no external forces act, these must be conserved. So the most fundamental thing is to instruct the program at a certain point, anywhere you want, to just write out the kinetic energy in a text form, so that one can check that if one removes all external forces, the total kinetic energy is the same. With the Lagrangian method, it's extremely easy to understand whether our parameterization, equations of motion and everything is correct. One more thing about parameterization. In general, structures that can be considered open loops, even if they have derivation, for example, as if here there was another joint attached to this point, to which another point was attached. Anyway, this was an open loop. Let's say, just in general, structures which can be considered open loops are very easy to parameterize because everything becomes just a sum. But closed loops, or anyway systems which exhibit at a certain point a closed loop, such as the very piston case, or a bridge in 2 dimensions, bridge which can be considered as a system, a sort of multi-pendulum whose extreme is attached again to another endpoint, a closed loop, because whether the first point and the last are at different fixed points or at the same is actually the same thing and introduces the same complications. When there are closed loops, it's a bit more difficult and needs some creativity. That's why I bring this example, because it's very important, and one can make some interesting considerations on how to parameterize this. For example, starting by parameterizing as if this point was constrained alone, then parameterizing as if this was alone, picking from the table of most common jointing mechanisms used in mechanical engineering, and then sees, okay, I'm left with the need to enforce a fixed distance between 2 points which already at their turn are constrained. What to do? Of course, good old analytical geometry is useful for something, because for example we know that the very compass is such an instrument that by intersecting 2 circles with 2 right radiuses, it automatically gives an intersection, and the of course more intersections, but with our local approach we know that this is not a problem. It's the intersection which is the only position for this to satisfy our condition of fixed distance here, fixed distance here, at the same time maintaining some constraints. There aren't many interesting 1 degree of freedom dynamical systems, except the piston case, for example, but we are going to consider quickly 4 of them. The simplest is the material point constraint to stay on a parameterized curve. Of course, it may sound strange, but already this example, which we had developed quietly and had implemented simulation of it with the GameMaker, was already a parameterized curve and not even a simple one. But of course, it was almost easier to do than to describe theoretically. Of course, in this case, in the generic case, we can think of a parameterized curve as a curve described as a vector valued function which depends on one single parameter. Okay, so vector x, 3 components which depends on one variable. It's extremely simple, because one can have many different types of parameterized curve. The simplest one is the polynomial parameterized curve, which we aren't going to describe because it's self-evident. We just have to apply this thing to obtain the velocity, and then one can obtain the kinetic energy by applying this formula. Since already in this cases calculations can become very bad here, and one can encounter mistakes even in this very simple case, because one can always forget something, and of course human error cannot be removed, it's already important to be able to use a symbolic calculation program, for which, for example, I prepared a script which obtains from the very parameterization. This is one material point, one parameter obtains automatically applying this formula here, which we have been dealing with in detail, obtains automatically the velocities, then of course the kinetic energy according to this definition, and of course obtains this A and B in a very comfortable way, and also the FQ. Remember that for the 1 degree of freedom case, the A and B become scalars, while usually they would be A matrix and B a vector. But we'll be doing this later. This is just apply the definition by assuming that we have a Q at the beginning and a Q dot, which are of course variables that are independent for an instant. Let's do evaluate all cells, and the program automatically obtains these quantities: the velocity, kinetic energy. This is just auxiliary, this is just substitution to avoid coming to very ugly expressions. So this one, you'll be using the same notation even for the more degree of freedom things, and that's all. To obtain the A and B quantities, one must insert in the simulation B equals A equals the FQ is this one, while the force is calculated here. For the viscous friction one, it's also to have the velocity, but that's automatically calculated here. Okay, so that's not a problem. It's also interesting and good to visualize. This is V, and for this very simple case we also draw the acceleration. Of course the kinetic energy can be done by summing the squares of the velocities components and multiplying by this, and it's very suggestible to write it in order that one can make a check. Let's run this simulation. The curve is this one, simple parabola in space, not even inclined. Of course, adding gravity and friction, things become more realistic. Using this script by substituting expressions of different parameterized curves, such as this one here, for example. This one here, whose expression is not even so complicated, something like this would be almost impossible to get right by hand. And such things one could do it with this program. If there are more like this, still 1 degree of freedom, of course, this distance fixed. Okay, it would be very interesting. Of course we don't waste time because it's too much theoretical. Very interesting curves to do the simulation with one material point is this spiral, for example, or other things. Another kind of interesting 1 degree of freedom case with 2 material points is this one. This point can go only on this line and this only on this. So 2 prismatic joints and 2 rotating joints. Interesting example that many situations can be parameterized in 2 different ways, but the preferable one is the one that doesn't need too much conditions. This didn't need any condition on this variable since the sinus and cosinus are self-repeating functions. Well, in this case, by inserting an x greater than L, it would be a crash, not possible, like square root of minus values and so on. Okay. Parameterizing is an art, we have said that multiple times, so one cannot pretend too much on that. We now progress to the piston case, so simulations QDD, 1 degree of freedom, piston 3D, run the simulate, it compiles correctly and everything, it has 3D graphics but doesn't use OpenGL, of course, I wrote that routine. Okay, when we have no, look at the kinetic energy, it's constant. Let's give more velocity to it so that we raise the energy level here. It's not too high and not too low. And while progressing its motion, the kinetic energy is maintained the same, of course, considering significant ciphers, because it is not exact integration, it's just almost exact until a certain precision. We can see how things go. Of course, the motion of the thing is interesting if this mass is higher. Now by pressing the N button, I raise the mass and see what happens. Here the rotation becomes faster and slows down again. Let me give more mass to it. Now the generalized forces are very interesting because one can push it. Look there, I'm pushing it, or I'm pulling it. You see, it becomes rotating faster here. Okay, let's give gravity and friction to, let's give friction to it. You see that the kinetic energy lowers. The software draws the velocity vector here. Okay. Look that red line there. Now let's give gravity. Of course, in order to have a real-time simulation, one has to raise the time step, which is not a very good thing because below a certain level it's not realistic. In fact, it's okay. I put also for this case the script with the calculations. Just has to open it. 1 degree of freedom, piston 3D, Lagrange calcs. In fact, while the parameterization is very simple, the calculations become awful, actually. It's such a disaster that you see, I prepared this example on purpose to show you how important it is to be able to implement a computer simulation with the Lagrangian method, where these derivatives can be done with finite differences, how important it is to know the personal computer and in general the personal computer. The interesting thing with the parameterization of the piston was, as we previously said, one can try to parameterize the point number 1 and express it. Then parameterize the second one parameterizes separately. But one knows that this depends on theta. But at what conditions? It's certainly the x of this is certainly this distance plus this distance. This distance is known, it's our cosinus theta, but we must add something. But enforcing the constancy of this distance, one knows from Pythagoras' theorem that in a rect triangle, this distance squared plus this distance squared equals to this distance squared. This is constant, so one can say that this constant squared minus this constant squared equals this. In fact, what a surprise, it's that. And we have parameterized it. It's a closed loop, very interesting. The calculations are a bit bad, but that's a very interesting dynamical system. Okay, now, a last thing on 1 degree of freedom systems, the bridge. The bridge can be very bastard because it's the very strict kind of closed loop. This is absolutely fixed, so parameterizes the position of this. It is very simple. One says that the second, if we say here is an angle called alpha, it depends on theta, we don't know how it depends, then this point will have position this one plus L1, of course this is L. Very interesting. The problem is that this alpha depends on theta according to this relation, that the relative distance between these 2 points, so between this and this, equals to R2. We explicit this, x2 equals, and at the system with this we put this expression. You realize that also conceptually the right value of alpha exists, therefore this distance is R2. This is not a function. One cannot find the solution of this equation and say alpha equals. This is not a function, this is a fucking nothing. But of course, you know the bisection method. One can find this alpha. But to say, okay, things found with the bisection method in a computer program can be, you can say alpha equals bisection method of this expression. But in a symbolic calculation you cannot. So with this you cannot do it. Also in a computer program you can always have this alpha found to any precision you want as a function of theta. To do derivatives you must use the finite difference thing, otherwise you cannot simulate a real closed ring, neither this one, neither that, which has more braces and more degrees of freedom. Let's see a little demo for this. Meanwhile, while I'm looking for it, let's say that I prepared this example of the simplest 3-arm bridge in order to show how important it is to be able to implement a computer simulation with the Lagrangian method and know how important it is itself the personal computer, because one can solve these kinds of problems which otherwise would be not solvable symbolical. Okay. When there is a solution, the alpha univocally exists. Hop now. Okay. Exactly. The passage from curvature this way to curvature this way, because there are 2 possible values of alpha for which this distance is equals R2, and there is a very delicate passage from the curvature down and the curvature up, and this change depends on the direction from which this point was approaching this change of direction situation. Must consider this. Imagine like a circle which is not a function, because there are 2 values corresponding to a certain x, even if this x is a legal value. In fact, there are two intersections. So although one parameter, this situation is very interesting and shall have to be dealt with in the second part during the numerical derivatives, where we have to be very careful by avoiding the situation of going outside the solution region. Here is alright. Oops, here is not alright. Okay. Okay, this was good and nice, and also very simple. It allowed to simulate us interesting dynamical systems, but of course now we want to simulate more interesting and far more practical mechanisms. Therefore, we need to extend the theory to dynamical systems which have more degrees of freedom. Since we already can have an intuition that generalizations are very easy with the Lagrangian dynamics, the best thing is to start from a one material point but 2 degrees of freedom mechanism, choosing one with whose parameterization we are enough familiar, do our deductions, and then simply see if we can just extend to an generic n degree of freedom mechanism. We already know that raising the number of points doesn't introduce any change in the Lagrangian equations of motion. And we also know that the presence of time-varying constraints, absolutely the greatest part of all mechanisms and all interesting things, contain time-varying, so-called time-varying frames of constraint, doesn't introduce any change in the Lagrangian. And once we can derive such an expression for a more degrees of freedom thing, we can say we are alright and start to simulate very most interesting mechanisms and conclude this first part of the video. Of course, there can be different approaches, but let us just outline how things works, to what notations one must be careful, and some basic mathematical rules to understand the derivation of the 2-degree of freedom system. Let us just adopt a mixed approach. One can, for example, start from considering the expression of the kinetic energy when there are more degrees of freedom. Take as an example the spherical coordinates, where we have 2 degrees of freedom. Our q will have a q1, q2, which are comfortable angle notation is a theta and a phi. We can give proper names to it, which anyway becomes a q vector, which is, we know what the kind of vector is. This is a real vector, this is just a list of values. Since there are more q's, trying to evaluate the time derivative of the position as a function of the generalized coordinate vector, we obtain this expression. This is nothing so stratospherical, it's obviously this kind. Don't get confused. This way of writing is a bit confusing because it doesn't say that these 3 coordinates and this has as many coordinates, as many number of degrees of freedom the system has. So always keep in mind that this can be rewritten this way: q1, q2, q3, q has many number of degrees of freedom, of course, but this is compressed notation. Okay, so kinetic energy would become such an expression where we would depend, of course, on the generalized coordinates. Just let it write, for example, this way: in this vector velocity per velocity is velocity squared. Of course, we are not going to waste much time, but the idea comes from writing one point constraint to a spherical surface and one position fixed distance in spherical coordinates. So in general we have f, I am not going to indicate anymore the time dependence, equals im a, which will depend on a q double dot. But since we don't like q double dot, we write all this as amper ddt vector as a function of the generalized coordinates and their rates of change. This is the same. Now we need that analogous of our operation which we did with the 1 degree of freedom thing. We are looking for a vector that to a small variation of a pair of generalized coordinates gives variation on our Cartesian coordinates of the point. This way, but producing vectors which corresponding to a certain combination instantaneous, certain configuration gives some vectors parallel to the local trajectory. Doing these operations certainly will do this. This is a vector. We performing this equation which we knew from the 1 degree of freedom thing can produce this kind of vector made of vectors as its elements. We are tempted to fold these operations considering that the sum of two vector quantities can be summarized without loss of information. But now be very careful with this also on books. Here, for example, be very careful. This, let's say, upfold operation can always be reversed and unfolded. So let's operate with this, but then remember that when you arrive at the good point to a formula which you like, you must know when you must unfold. This can always be unfolded. These are two vectors. Okay, the sum is itself a vector, but it's expressed as a sum of two vectors, so no loss of information. This is analytical derivative expression, so these two components don't disappear. Okay, we multiply both sides by this, here, and from now look it on a good book. One can consider the same reasonings. One can generalize easily that result which we had already been using with the 1 degree of freedom thing, that this position derived with respect to the generalized coordinate is equal to the velocity derived with respect to the rate of change of the generalized coordinate. This works component by component. Be very, very, very careful with this. Also, this can be upfolded and unfolded versibly. This way, be very, very, very careful. Operate all the things usual which we did with the 1 degree of freedom version, and when you arrive at the right point here, when you have this I thing, everybody uses a different notation, of course, so be very, 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 very careful. When you arrive here, you remember that you still can unfold this back. Follow carefully what operations you are doing. When you arrive here, remember that here you could have unfolded. This can be unfolded. Okay. So also this can be unfolded, and this becomes a system of Lagrangians. So, okay. Generalization is completely immediate. The FQ, you already know what it is. And that's all. Just look it up on the book, but be very, very, very careful with this upfold, unfold thing. And remember why this is true. Keep in mind this figure, if anything. And so on. In general case, we have as many equations of Lagrangian equations of motion, as many degrees of freedom of the system. We must note that when we express these with the explicit time derivative, we will have for the usual thing of deriving, for expliciting the time derivative this way, and writing all of these with that explicited notation, which is the actual procedure to calculate ddt, expliciting that, you will end up doing You can also do some substitutions, end up with an expression of this kind. Okay, you can bring all these, which are all known terms, rewrite, leave this matrix by vector of q double dots here, and you realize that a general simple computer simulation procedure using the Lagrangian method will be of this kind. Initial conditions with q0 and q dot zeros. We calculate known terms, we calculate another vector which we will call b in our single degree of freedom case, it's one scalar. We calculate the q double dot and we do the instantaneous update of the system, and we represent graphically the situation. Piston or the groove manipulator or the point on a car or many things. So the procedure is completely general, and the whole thing depends only on the parameterization of the system, which the passage here is completely mechanic, but of course for not too complicated situations a symbolic solution by expliciting this and inserting in the computer program code the very mathematical expression, you can allow anyway to do cool simulations. When things get more complicated, in the second part of the video we will see how to do a procedure which does all these derivatives numerically. First we are going to do some simulations of 1 degree of freedom systems, then introduce the more degree of freedom systems, and then the generic case and the matrix notation, which is completely general. A matrix, this plus this is the B term. Okay, using our Lagrangian, our equation of motion for the Lagrangian dynamics is just very easy. We just have to categorize well and write down well those very few mathematical rules of vector valued and vector variable functions which we use in a clear way. Okay, so to find the kinetic energy is very easy because this is a given, the parameterization is given, and we write it this way. It depends only on the generalized, on the vector containing the generalized coordinate. That's why this is a vector variable, vector valued function. Very simple. Think of it this way. If you prefer the kinetic energy, we only need the velocity for each point, so it's very easy. We must to consider that it's the time derivative of the position, which is a vector valued one vector dependent function, and procedurally it's written this way, and this equivalent, but okay. For simplicity, instead of writing just q, instead of writing usually like qt, since we're interested mostly in computer simulations, instead of writing this, we usually just write it q. This way. I observe this here. To make the notation smarter, we avoid these notations because it would become just very long and also useless. So the velocity is given by this, all as a function of the generalized coordinate vector and the rate of change of generalized coordinates. The vector containing the rates of change of generalized coordinates, and that's all. Now, very important nota bene is that an extension of this rule to a vector valued function when there are two vectors, two of course completely independent vectors as variables, although actually it may seem that these are just lots of variables together. The rule to derive thus grouped thing is this one. This sometimes causes a lot of confusion. That's why I wrote it here. I wrote a nota bene here. I put this arrows here to indicate that this rule, if you understand this, most confusion is not the Lagrangian dynamics is very easy, but the notation and the fact that there are lots of function inside function can cause some confusion. But besides that, okay, the compressed notation for the Lagrangian equation of motion to find the q double dot from eventually find the q double dot vector starting from the kinetic energy expression, which is of this kind, is a compressed notation. Very confusionary. Of course, avoid this notation. Its explicit notation is this way, of course. One equation for each degree of freedom, and here q1, 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 q2, 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 and so on, and number of degrees of freedom. As many equations as many numbers of degree of freedom. How to calculate this, we saw it already, or anyway we see it later. It's just a scalar, not so important. And then to plug this into a computer and to explicit the DDT according to this very important rule, here is the explicit notation. We replace this ugly expression, we perform this derivative for each of them, we call it f key, so understand the substitution. And of course we write down this thing. The DDT becomes this because this has become a vector. This is a compressed notation. Be very careful. You see here this vector. This is vector value. This rule must be explicited even more, and it becomes naturally a matrix. This way, which is, try to explicit this rule, is the sum, try to explicit it better, it's the sum over key of this derived with respect to the keys and multiplied by the q dot keys, and the same for this. We must sum here all over k. Now don't force me to rewrite it, just insert here the green screen thing. And the comfortable notation for this is the matrix thing, because when you write the summatory, you realize that you can pick out these and express it in a matrix vector multiplication for. Don't remember one part, other part. Don't ever make this mistake. This operation, this way, this is q depending on t, q depending on t. Two components, two members. So one member summed with the second member, and the other side of the equation is very simple because it's already just a sum of two vectors, a vector made by doing these very simple partial derivatives, and of course the q's the FQs have been, we assume, calculated before, because that's really simple. And that's all. That's these few mathematical notations and rules of the chain rule from derivation applied to these vector value, the vector variable functions, must be handled correctly. And after all, that's very simple for the computer program. Okay, very good. And this notation, why is so important? It's so important because you can express this in a compact notation, which is the vector containing two q dots. You can say that it's the inverse of this matrix. Let's call it A. Per a vector which let's call B. B vector is the vector formed by summing this with this and this brang here, so with negative. Since these are all known terms, these can be multiplied together at once. Brang here summed with this, and we obtain a vector of known terms. We have this matrix, of which we take the inverse, and we can express the whole Lagrangian, the whole equation of motion for the system this way, and this can be done with the usual stepping, which was this, as we told. So we calculate our simulation will be made from calculating the q dot, as we did from the material point. We calculate this pseudo acceleration, we apply this to, we do this at each step, and so on. Of course, in order to find this correctly, we may need to calculate also external forces, if we consider also external forces and so on, such as an external force applied to this system here, and maybe also here, x1 vector affects to one vector, and so on. In the simulation software, I did this way. Now the nice thing comes that just as for the material point, we could do finite element thing by considering instantaneous approach. In order to be able to make it for this thing, we must do numerical derivation. T may be left a symbolic expression, because after all the very parameterization is one assumes that the parameterization is really not much to require. That's the parameterization is like setting up a construction, clicking with the mouse. It's sort of a definition of what I want to simulate. So pretending that the user in a simulator software inserts the parameterization into thing is not much to pretend this way. x1 equals x2 equals, it's really not much to pretend, and that's okay, since this is symbolic, but this function can be evaluated anywhere. One can do all this in a software, one can do all these derivations numerically, and since all these become constants, all this becomes a finite element method. Cool. So actually, after having discussed these things, one can write directly the expression gives the q double dot thing. This way almost resembles Newton per second, or ta-ta, done. The A calculate. Here we have one of the most classical examples of a 2-degree of freedom dynamical system, the spherical pendulum. Of course, it's a bit too academical as an example, but we have presented it in this 3D graphics fashion. With the more degrees of freedom situation becomes absolutely, but I say again, absolutely necessary to be able to use a symbolic calculation program and prepare carefully a script to find the expression, because already in this case calculations become very bad. Let's get it evaluated. Okay, it's not so bad, but it's bad. It already starts to become convenient to forget expliciting expressions like Q equals, Q1 equals, Q2 equals, but insert a matrix form, keep such a matrix in the computer program by putting this, doing the enlarged matrix, and send it to a linear system solving procedure, very simple, and thus find the Q double dot, the vector containing Q double dot, and then update system. You can study these examples quietly, which I put on SourceForge. So, okay, let's see one of the most classical examples, the double pendulum. Okay, some pretty graphics. Generalized coordinates, the kinematics. Of course, one should now watch that in this case where there are no external forces, the kinetic energy is conserved. In these programs, since I couldn't write a list of the keys, one should just look up in the code this section dedicated to the interactive things and the interattività, and see what is for what. So for example, where one can activate the gravity and so on. Friction, gravity, and so on. Let's run the simulation again. A remarkable articulated body. The most general case is where both of these points are actually spherical pendula, but that's becomes too complicated, and that's for the second part of the video to do with numerical derivation. Of course, very simple to parameterize, but the calculations become awful. This is yet affordable. And if I remove gravity, everything becomes inertial. The motion still remains quite remarkable. Special effect of the tracing line is very useful here. I will try to implement also with my routine so that no OpenGL is needed. But this is nice 3D graphics. One can see that the motion is in a plane because Lagrangian dynamics doesn't really care about how many dimensions there are, 1, 2, or 3, but of how many parameters there are. So here there is a script for the calculations. Here there is a whole folder with interesting examples. The mass Polley example from the book is for the second part because it requires concepts of advanced parameterization, because there is a wire whose parameterization is quite bad. There are some other examples. For example, for the spherical pendula, there is also this example with simpler graphics. This is an example with 3D graphics but no solid representation. We have the with gravity and no friction, so we have these typical figures of the spherical pendulum, which it traces by moving. This is a bit too academic and theoretical, but I showed it to you. the 3D graphics version is here, and of course it's much more evocative. Okay, the simulations are here. We have one of the most interesting things is I did some other examples here, among which a generalization of the spherical pendulum thing, which is a rigid rod freely floating in 3D space. Because of course Lagrangian method is also good for open world examples. In fact, this is the first step towards rigid body simulation, which is for the second part, but this doesn't require, the rigid rod still doesn't require advanced parameterization techniques. In fact, we have 5 degrees of freedom, 2 material points, one here, one here. The parameterization, the calculations start to become quite ugly. In fact, I have prepared also for that the script. Probably here I made some mistakes by hand, but okay. The other example, a little bit simpler, as you can see, is that truck example, where of course we have just 1, 2, 3, 4, 5 degrees of freedom, but this can move also only along an x. This angle is fixed, and this can rotate, and this is a spherical pendulum, so not even so terribly complicated. Another interesting example is the groove bridge. This one, which comes in 2 different versions. One which considers that this can only go float, like right, so that this can just have a certain angle here, and this can move right and left. This is the very simplified version. 2 material points, and this is the situation. 1 angle, 1 distance here, 1 angle. Very simple. Also, this is an academic example, very common and famous. Real groove bridge, which has a theta angle and a phi angle here. So a spherical pendulum which is attached to a point that can have different positions, different distance from, which stays on a line. Prismatic joint and the reduced universal joint. This is the groove bridge. Here is a scheme of the scheme of the parameterization, 3 degrees of freedom, 2 points, and the concept is this one here. As we said, we consider with this relative thing, we start from the simpler one, we parameterize with respect to this position, the position of the next point. So x1 plus something very easy to parameterize.